So let's continue with the last talk of this morning session by Vladislav Vysotskiy on the isoperimetric problem for convex halves and rate functions of random walks.
Thank you. So in this talk, I will be dealing with convex halves of random walks in the plane. So here is the notation. ST is the kth step of a random walk on the plane. So it has ID increments x1 and xp, which are random vectors on the plane, and we'll look at the convex hull of the first n steps of the walk, and we include 0 just because this makes some formulas nicer. For my results, this inclusion of 0 doesn't change. So Cn is the convex hull of the first n steps of the walk, including 0. So this is a random polygon, and we are interested in different characterization of this random polygon. So there are many known results about this quantity. You can describe it in different directions. So for example, you can look at its numerical characteristics like perimeter, number of vertices or diameter, and so it all started, so there is a huge list. Just to quickly mention, it all started with a very nice formula by Spitzer and Widom, which gives an explicit description for the expected perimeter. Beautiful formula. This is one type of results, and apparently there is a similar sort of similar formula for the number of vertices by Baxter. This is one type of results. So the expected values of some quantities describing the convex hull. So the other type of result is a limit theorem, but surprisingly, there are only overall, there are very few limit theorems in the area. Somehow, one of them is given by Andrew Wade and his co-authors, limit theorem for the perimeter, and somehow the same techniques works for the diameter. But interestingly, there is no limit theorem for the number of vertices. So that's a simple, apparently innocently looking quantity, but this is not known. This is one type of result. The other type of result is more geometric. You try to understand what's the shape of your convex hull, and in particular you can analyze the what we call absorption probabilities, the probabilities that 0 is included or not included in the convex hull. And there are few results by myself, Dima Zaporozhets and Zahar Kablichka, characterizing these points. So that's a general overview. The random walk is two-dimensional. There are many generalizations to high dimensions. I set these aside for this talk. And in this talk, I look at the remaining reasonable characteristics, which is the area. So for the area, so let's denote it by AM. We can find explicitly the expectation. It's a similar type of result, similar to that Spitzer and Widom I raised at the previous slide. And then you can write down limit theorems for the area, and they easily follow from the invariance principle. So, for example, if you assume if the steps of the walk have finite variance, then an scaled by n to a certain power converges weakly to whatever you can use from the invariance principle. For example, if the walk is 0 mean, then the convex hull goes in square root of n in one direction, square root of n in another direction. So the area scales as n. And if the mean is non-zero, so the random walk extends in the order of n in one direction and in the order of square root in the second direction. So it's n to the 2/3. So the scaling is pretty natural. And you can do different things. You can do either law of iterated logarithm for the area. This is the recent result. And we are interested in large deviations of the area at this scaling, n squared, as opposed to n to 1 or 3 halves. And this, we will see that this is the natural large deviation scaling. Okay, so I will need a couple of standard notation, some standard notation to introduce my first result. So we need the log moment generating function. So we take the Laplace transform of our random vector on the plane, take the log, so that's the convex function which I call k, and the rate function of this random vector x. Oops. So what should I do? Okay, so that's the rate function. So if you never saw this, or if you forgot this, so this is what to keep in mind. So this is something convex, which is non-negative. It has it's minimized at the expectation. So typically, this is the example to keep in mind for the whole talk. This is just a paraboloid with a vertex at the expectation of the increment. So this is the rate function of the random vector, and I will give a functional version of this result, which is what is called Magulsky large deviation principle for trajectories of random walks. And so what is interesting here, this is maybe one thing to remember, is so here this, unlike the usual Cramer's large deviation principle, which only assumes existence of exponential moments only in the neighborhood of zero, so for certain reasons, which are not really technical, but actual reasons, we need Laplace transform to be finite on the whole plane. And then we look at the trajectory of the random walk. So we have a bunch of points from 1 to n, these are SKs, and we form a function on 0, 1 by linearly interpolating between the points, as usual, so they are piecewise linear trajectory. And then Magulsky results says that if you take the trajectory, which is now a function on 0, 1, normalized by n, as usual, so then these trajectories satisfy the large deviation principle in an appropriate functional space. And the functional space will be the space of absolutely continuous functions, which start at 0. And the rate function will be this one. I denoted by IC to stress that this C corresponds to the space of continuous functions. And this is the integral of the rate function of the vector, computed at the velocity of my test function h and integrated over the line. So just how to think about this, this IC of h is just the energy of my function h. H is an absolutely continuous function which starts at 0. And this means that the probability that my trajectory normalized by n looks like h is the exponent to minus n energy of h. This is what it means. What this means. Okay, and this Magulsky results, which gives us the large deviation principle for trajectories, lets us easily obtain large deviation principle for the area. So under assumption that the Laplace transform is finite in the whole plane. So then the theorem says that an divided by n squared, so the scaling unpromised, satisfies the large deviation principle with a certain rate function. Let's keep it here for a second. And what this means, that the probability that the area is atypically large, an times n squared, so it's of this form, e to the negative n times the rate function for the area. So this is the LDP, and as usual for most LDPs, we can say that given this event of large deviation of the area, the trajectory looks like one of the minimizers of this function. Okay, maybe I don't have much time, so I will say that this easily follows from the Magulsky large deviation principle using the what is called contraction principle, which maps one LDP if you have a continuous function between two spaces. So this was a sort of introduction into this isoperimetric problem, and now you see if you want to understand these large deviations, we need to find this minimum. And let's look in detail about this minimum, and let's try to solve it. So this is the whole point of this talk, trying to solve this problem, and I call it isoperimetric type problem, because what are we doing? So we try to minimize this energy of a trajectory, and we minimize over which kind of trajectories? The trajectories which are absolutely continuous, start at 0, and they have prescribed area of the convex hull of the image. So this sort of reminds us an isoperimetric problem, and instead of the length function, we have this funny function which is sort of like energy function. Okay, so this is the any questions so far? Okay, so there are two approaches, and let's say one is, let's say, more or less straightforward, and the other one is more tedious. So I'll quickly go through the first approach just to show you some results, so you have an idea about the minimizers. So first is try to minimize this integral of this isoperimetric problem, the unusual one, trying to relate it to something which is more usual. Let's reduce it to some known isoperimetric inequalities. So for the moment, let's do the easy case. Let's assume that the distribution of x is rotationally invariant. For example, think that it's zero mean standard Gaussian. Like mu is 0 in this picture. Then the rate function is a radial function, depends on the norm of our vector. Then this is the energy. We can write it in terms of the radial function, and you remember that the rate function is convex, so its radial function is always convex. I can do the Jensen inequality, and here I have some function and compute it at the length of my absolutely continuous curve. And I'd like to lower bound this by something, and this under, and I have this constraint. And then this transfers into what is known as one of Coulomb's problems. What is a planar curve of fixed length which maximizes the area of its convex hull? Of course, the answer is what you expect. It is a half circle. So you make the half circle, and then because you don't need to go back as in the classical Dido case, but this looks like a version of Dido problem. It's not exactly like this, but this is like a Dido problem for convex hulls. And then when you plug in the thing back, you get the initial answer that if the distribution of increments is rotationally invariant, then the minimizers, the optimal curves, which maximize the area, are parameterizations of half circles of certain radius, and you need to move with constant speed in order to have equality in the Jensen's inequality, which I showed you. So that's right there, clear idea, and you can work the things out. So you see that so here we do the rotational invariant case. Maybe you can just cover some linear transformations. So the other interesting bit, is to get away from this rotation invariance, and this will be sort of non-geometric, which corresponds to the case where this mu is non-zero. Then this is sort of some weird energy functional, but then you can work this out in the shifted standard Gaussian case, and then the minimizers will be constant speed parameterizations of circular arcs. So basically, if mu goes like this, then the minimizers will be circle half arcs, either this one or this one. And this is again by reduction to some other known isoperimetric inequality for for convex halves. So this we can write down some explicit answers in some reasonable cases. Okay. At least we can do the Gaussian case completely, and rotationally invariant, and some variations. Okay, so this was one approach, and the second approach, which is, let's say, more technically involved, but this is how it started at the beginning. So it's to try to solve the variational problem, the isoperimetric problem I showed, using variational calculus ideas. And so two steps to do. So first is to try to do reduction to convex, to the convex curves, and then minimize over the convex curves. So let's quickly go through these steps. So step one is to show that we can minimize over convex curves, and here we'll do reduction by using what is called convexification of planar convex curves. So basically, the picture is sort of self-explanatory. So it says that if you have a polygonal line which consists of some linear segments, then we can convexify it. So rearranging the segments into increasing or decreasing order by angle. So you keep the lengths and obtain a boundary of a convex polygon, like on the picture. This is when you work with polygonal line, and for arbitrary, let's say, absolutely continuous, in my case, curves, we can do approximations. So when you do this, so this is based on the ideas by Spahan, Farin, Makaye, so from these years. So if you do approximations, so for any absolutely continuous curve, you can find a convexification such that when you do this procedure of convexification, nice things happen. So first of all, the area of the convex hull does not decrease. So you try to minimize the energy while possibly keeping or increasing the area of the convex hull. So this is what convexification does. And second thing, convexification does not increase the energy. Somehow, this is very clear because the energy is an integral, and when I do the integral, so here when I convexify, I just take my, I follow the path of polygonal line in different order, so the integral doesn't change, at least in the discrete case. So the inequalities are in the right side, and also the same is true for the signed area. Signed area of the curve is just the, which is not necessarily convex, is what you have from the green formula. Okay, so with this convexification procedure, so it says that we now can reduce our variational problem to solving the same variational problem over convex curves, for which we can express the area of the convex hull using the green formula. So that's an integral. So h is a now vector coordinates x of t and y of t, and we minimize one integral of a cost function of the velocity of the curve given fixed another integral in terms of the curve and its derivative. So, and then this is a classical area of variational calculus. So, in variational calculus, they need to prove existence, but this already follows from the variation principle. So, this the minimizer exists. Let's try to find it. How do we do this? Well, we form the Lagrangian. We have an extra term with the Lagrangian multiplier coming from the constraint, and we try to solve the corresponding Euler-Lagrange equation. Well, so for some reasons so that's a technicality assumption. We need to assume that make a certain assumption on the support of the vector. Let's set this aside. But how we do the Euler-Lagrange equation? So we write an equation, and we solve it. But so the main difficulty is that we can do this only when we know a priori when the minimizers are smooth. And the message is that this is not always true. There is something which is called Lorentzius phenomenon, which says that there can be non-absolutely continuous minimizers which don't satisfy the Euler-Lagrange equation, and we cannot find them naively by solving the Euler-Lagrange. Well, fortunately, there is a way to overcome this, what is called Tonelli's partial regularity theorem, which says that the minimizers are smooth if the Lagrangian is strictly convex. And remember, the Lagrangian comes from the rate function, and it turns out that under the assumptions of finiteness of the Laplace transform on the whole plane, the rate function is strictly convex. Okay, so maybe, do I have?
You started a bit late, so.
Okay, so thank you. I'll just, yeah, my main slide is the next one, so.
Stop immediately.
we are converging there. So basically, what we need to do. So this is the Euler-Lagrange equation. This is some abstract thing. So why do you expect to work with it? Well, and it turns out that we can solve it explicitly, which is quite. I didn't expect this from this general setting. So, and this is because you remember that the rate function is the Legendre transform of the log Laplace. So, and this says that the inverse of the gradient of the rate function, which is exactly the gradient of the log Laplace transform. So, and this is the first Legendre equation, and you can invert it here, and after a few lines, we end up something which shows us that, okay, let me go into the conclusion, that the dilated and rotated minimizer belongs to a shifted level set of the log Laplace transform. So the second message is, surprisingly, we can solve the Euler-Lagrange equation explicitly. And go into the theorem. So the theorem says under assumptions we have, every minimizer is a smooth convex curve obtained in the following way. So take a level set, certain level set of our log Laplace transform. So log Laplace is convex, so the level sets are bound, so are convex curves. So that's a closed convex curve. So find certain diametrically opposite points at this curve, which will be endpoints of my minimizer. And parameterize this half arc with certain speed. And this is the answer. Well, and then you do whatever you saw in this computation. You dilate and then you rotate. And that's the answer. So why it's Why it's reasonable, how this relates to something else. Apparently there is an old result of Busemann, and I want to finish this comparison against this result of Busemann. So look at the norm, which is generated by some symmetric compact convex set, which is a unit ball in this norm. And apparently, if you try to solve the isoperimetric problem in this, with respect to this Minkowski length, so then it turns out that the solutions to the isoperimetric inequality with respect to this Minkowski lengths, which enclose the maximal area. So now I'm thinking about not convex hulls, but closed simple curves. Then a result by Busemann says that the solutions parameterize the boundary of the polar set to the unit ball in the Minkowski norm. So and then there is a direct analogy, because for basically what I do, you remember my energy. In my energy, I integrate the cost function of the computed at the velocity of my random walk. So in my case, for random walks, the cost function is the Legendre transform of Laplace. And for Busemann, we can write the cost function, which is the Minkowski norm, as just the Legendre transform of the convex indicator function of the polar set. So that's a way to describe the things. And then the results are very similar, because in my case, so what we at the end do, we look at the level sets of the Legendre transform of the cost function. So this function is convex. So the level sets are convex sets. Their boundary are convex curves. And here for Busemann, we parameterize the whole boundary. And for random walks, we parameterize certain sort of half boundary, certain arc of the boundary, because this is a perimetric problem for convex hulls. Okay, perhaps it's a good time to stop, and thank you for